So we learned yesterday about Sahala, sine function, it's a new parent function. You should be able to sketch it very, very quickly. There are a couple things here, though, that are specific to studying sine waves or wave functions in general. Okay, so we got our standard transformation form. We know what A, B, C, and D do, right? That's no mystery what A, B, C, and D do to any function, including the sine function. But we actually can come up with special names for the A, B, C, and D based upon what it does to the wave function. So the absolute value of A, that's the number in front. It could be positive or negative, but its magnitude we call the amplitude of the wave. Okay, it's the amplitude of the wave. Another name for the amplitude is the wave height. Okay, so if you want to add that, let's modify that. This is also the wave height. Okay, so if you come up here to our little sketch of sine, and you want to figure out the wave height, it's the distance from the sinusoidal axis, which is the x-axis to begin with, to the top. This is 1 unit. So the wave is 1 unit tall. It could also be from the sinusoidal axis down to the bottom part, which is also 1 unit. Okay? It's also 1 unit. If A happened to be 2, like if this were 2 sine of x, what does the 2 do to any graph if it's out in front? Well, it vertically stretches it by a factor of 2. That's going to make the graph go up to 2 and go down to -2. Okay, so here would be 2 up here, and now the wave height would be 2. So that's pretty cool. The A value still is your vertical dilation factor, but its magnitude is the amplitude. Now, as I mentioned earlier, as I talk, my sound reaches your ear through a sound wave. It's a wave function, much like sine. What would increasing the amplitude do to the sound wave as it approaches you? Like, what would be the difference in a sound wave between an amplitude of 1 and an amplitude of 2? Very good. It would be louder. It would be louder. It would be the same note. Like if I'm speaking to you in a monotone middle C, changing the amplitude doesn't change the note. It changes how loud it is. Okay, it doesn't change the pitch. It changes how loud it is. So, and you can remember that because they actually have machines that you can plug instruments into that increase the amplitude of that sound. They're called what? Amps for short, right? Amp is short for amplifier, which is short for amplitudifier. Did you know that? They're really called amplitudifiers, but we call them amps for short. All right, if we look at B, B is still your horizontal dilation factor. If B is greater than 1, it's going to compress it. If B is less than 1, it's going to stretch it. So you could imagine playing the sine wave like an accordion or like a spring, right? You make it more compressed or stretched out even more. That is going to affect the what of the sound. If you change its wavelength, or you change its period, or you change its frequency, what? Well, you do change its frequency. Frequency and period are reciprocals of each other. Wavelength and frequency are reciprocals of each other. So changing B changes the period, which also changes the frequency. And the frequency of the note determines its pitch, right? Every note, okay, on the scale, do, re, mi, fa, so, has a different frequency, okay? So when you change B, you change the pitch of the note. It's actually becoming a different note, all right? Now, what does B give us directly? This is important. The magnitude of B, which is the absolute value of B, don't forget this. It gives you the number of cycles in 2 pi. People forget that. B gives you the number of cycles in 2 pi. So what's the default value of B? In the parent function, what's the default value of B? 1. So how many cycles are we going to see between 0 and 2 pi for the graph of just plain old sine of x? 1, right? That makes sense. It's once around the unit circle. But if I change that to 2, I'm vertically compressing it by a factor of 2. So now I'm going to see 2 cycles between 0 and 2 pi, where previously I saw 1, okay? If that was the 1/2, I would stretch it horizontally by a factor of 2, and now I'm only seeing a half of the cycle between 0 and 2 pi. Okay, so does that change the period? It does. The number of cycles in 2 pi will change the period. So let's jump down here. P is the period. We can find the new period if we know what B is. If b is really the number of cycles in 2 pi, then we can say that the new period is 2 pi over that value, right? If b is truly the number of cycles in 2 pi, then the new period should be 2 pi, the default period, divided by how many we're trying to squeeze into that space, right? That makes sense. If you have a space of 1 foot and you're trying to fit 3 equal parts into it, each of them would be 12 divided by 3 or 4 units long, right? So 2 pi divided by the absolute value of b. If b were 2 pi divided by 2 would be pi. The period now would be pi. We go from 0 to pi for the first one, pi to 2 pi for the second one. If b were a half and we stretch it by a factor of 2, what's 2 divided by a half? It's 4 pi. Now it takes twice as far, 4 pi, to see one cycle. Got it? So b is not p, right? B is not the period. B gives us what directly? It's not showing up here. B gives us the what? The number of cycles in 2 pi. But we can find the new period by doing 2 pi over b. Now, you're going to see that sometimes we go the other direction. B is also 2 pi over p. That's important if we have the graph and we're trying to go back to the equation. Okay? Very, very important. We get b from the equation, we need p for the graph. So b is also 2 pi over p. They just switch places in the equation. Got it? They're related to each other by that equation. Okay.
Are we going to use the same equation?
Oh, absolutely. Yes, we will. Okay. C. C is still your horizontal shift, but because we're talking about wave functions, you can talk about the phase of the function. If two sound waves are coming into each other, but they're out of sync with each other a little bit, we say that they're out of phase with each other. They don't line up perfectly. They're out of phase with each other a little bit. That means that the one is shifted horizontally from the other. So I'm going to start referring to the horizontal shift as a phase shift, and everyone's going to understand when I say phase shift, you'd be, oh, the horizontal shift, left or right. Like the moon has phases. The moon is going through a phase, and it may be in a different phase than what you're going through, right? I'm in my terrible twos right now, but the moon is in the gibbous phase. Okay? Waxing gibbous. You know the difference between waxing and waning? That's what the moon does. And the gibbous moon is like the 3/4 moon. Yeah. All right, cool. Y'all know y'all's moon trivia. Now D. D is still your vertical shift. It's going to move the graph up, down, up, down, up, down. But what important feature does that change? It changes your sinusoidal axis, remember, which by default is the x-axis. So if you want to know where the new sinusoidal axis is, it's always going to be at y equals d. The sinusoidal axis is always at y equals d. That's going to be very important when it comes time to sketch these graphs, because you'll notice that when we sketch the graphs, one of the first things we do is sketch our sinusoidal axis, because it gives us a reference point for the height of the wave. Above and below that point, we go a value. All right, so every single one of these, A, B, C, D, has like a new name associated with it or a new idea associated with it that you have to know. All right. We already did example 2. We did example 2 right here. So if you want to just copy this and paste it down here, for example 2, boom, you could do that. It says to list the curvature changes. Let's go ahead and list that too. I'll get rid of the green one. We have a couple of other things that we can mention. We said the domain was all real numbers. We said the ranges are between -1 and 1. You actually have local maximums. Local max of y equals 1, which is also your global max of y equals 1. You also have these points right here. Your axis points are where the curvature changes. The axis points are where the curvature changes. What do we call those points? Where the curvature changes. We saw it on the logistic functions. We saw it when we studied x cubed. Let's look to the left of there. To the left of 3 pi, the graph is concave down like a frown. And then to the left, to the right of 3 pi, it's concave up like a cup. So it goes from a frown to a smile. Do you remember what we call those points where the curvature, the concavity changes? What's that? No, no. Louder. Inflection points. There you go. Very good. Thank you. Those are inflection points. The axis points are the inflection points where the curvature changes. We also talked about the symmetry of sine. Sine was an odd function. It has origin symmetry. So I think that'll conclude everything we need to say about sine. The period is 2 pi, of course. What's the end behavior? We didn't talk about end behavior. What would be the limit as x goes to infinity of sine of x? What's that? I don't know. What does that mean? That means if we hop on the graph of sine and we head out to the right forever and ever and ever, what are the y values doing? Are they increasing to infinity? No. Are they decreasing to negative infinity? No. Are they tapering off towards some specific value like a horizontal asymptote would do? No. What are they constantly doing? Going up and down. What's the word I used yesterday? It starts with O. Oscillating. Yeah. They're oscillating continuously between two fixed values, one or negative one, one or negative one, one or negative one. So is there a limit? If I ask you for the limit and they oscillate constantly between two values, what would you say? D, N, E. Yeah. Remember, limits can fail to exist for lots of different reasons. That's for both of them. Yeah, that's the left-hand behavior as well. The limit as x goes to negative infinity of sine of x is also D and E. But it's for a very specific reason. We'll call it by oscillation. Remember, the limit doesn't exist at a vertical asymptote either. Or for x squared, it doesn't exist because it increases to infinity. This doesn't exist not because it increases to infinity, but because it oscillates between two fixed values. Okay, I think that's good. All right, now we're going to meet the partner in crime for sine of x. What was the other sinusoid that we said at the beginning? Cosine. It's the only other one that has the word sine in it. Now, we can make a table of values from 0 to 2 pi, but I'm going to skip example 3 and go straight to this right here. Here's what cosine looks like. At 0, cosine is 1. Okay, we'll just mark this up. At 0, cosine is 1. What is cosine of 0? 1, okay? Now we'll come over here to pi halves. What's cosine of pi halves? 0, right? We're on the x-axis. And now we're at pi. What's cosine of pi? Negative 1. Good. This next axis point is 3 pi halves. What's cosine of 3 pi halves? 0. And then once around the unit circle at 2 pi, what's cosine of 2 pi? 1. There is a single cycle of cosine once around the unit circle. That's going to be your new parent function. It's also a periodic function. It's also a wave function, okay? But unlike cosine that starts on the axis and ends on the axis, cosine starts high and ends high. So if you think about these 5 critical values, these are your quadrantal angles, right? Your quadrantal angles. Those are your 5 critical values. How can we remember that what cosine is? Well, C is for cosine, and it's high axis, low axis, high, which if you do the mnemonic makes what? Chala. Chala, just chala. The last H is silent, but it's there, right? The last H is silent. Or you could say chala. No one's ever done that. Chala. I just call it chala, and I know there's an H at the end, okay? So the C is for cosine, and then here's our 5 critical values that follow. High axis, low axis, high. That's cosine. So you got Sahala and his partner in crime, Chala. Thank you for saying it. Yeah, Chala. Chala. All right. And of course, the pattern continues on and on and on and on. So let's jump to example 4 and see if we can sketch cosine using the Chala method. So I'm going to give myself a y-axis, not with a highlighter though. Stupid highlighter. Y-axis. Let's give ourselves a x-axis that goes out pretty far. Maybe not that far. We need some room to write. There you go. Okay, I'm going to scoot this over somewhere in there. All right, cosine, like sine, hits a high point of 1 and hits a low point of -1. So you can put those on there right there. There is a sinusoidal axis that runs right through the middle, but it's just the x-axis by default. So you don't even really have to sketch it. But I want you to know it's there. Come out here a little bit less than halfway on your graph and call that 2 pi. And then bisect that and call it pi. Bisect that and call it pi halves. You're going to want to have your critical values put down first before you sketch the graph. Don't just draw what cosine looks like and come back and label it. You want to get your x-axis lined up. That's 2 pi. Half of that's pi. Half of that's pi half. Now, this distance right here, this is what I'm going to be looking for when you sketch your graphs. Is your distance uniform between your quarter cycle counting intervals? That's what this is. This gives us our quarter cycle counting, not just interval, but distance. Interval/distance. And that's the distance that you need to preserve now between subsequent critical values, okay? So now I can come over here, I can bisect that, and I'll call it what? 3 pi halves, yeah, and then of course we got 0. So this is what I call setting the table. You set the table first. You get your axis down, you get your high point, you get your low point, you get your critical values labeled and spaced correctly, okay? You set the table, and now you put the food on the table. How do you put the food on the table? You put your critical values. So it's high, axis, low, axis, high. Okay? You put the food on the table. Now, the fun part, right? Why do we do all this? So we can eat. Now you connect these with quarter cycle arcs, okay? Take your time doing them with quarter cycle arcs. If you want, you can turn the corner a little bit because it is going to keep going. And there you go. You have one cycle of cosine. I'm going to copy this now. And what can I do to continue on? I can just paste. I can line it up right there. Boom, paste. And then I can come back and delete the y-axis. And if I want another one, I can paste. Line it up right there. Boom. Come back and delete the y-axis. And I can do one on the other side too. I can paste. Looks like that. And then come back and delete the y-axis. Now, if I want, I can also come through and change. Why is it not deleting? Oh, okay. Thank you. Yeah. I did it as an image. There we go. All right. So we can come back through here if we want, and we can actually change the x values, which we want to do. Change the x values. Let's change all the x values. All right. How would I continue labeling the new x values? Well, what are we counting by? What's our quarter cycle counting interval? Every critical value is how far apart? Pi halves. So we can just keep counting by pi halves. Let's keep counting to the right. 1 pi halves is where I'm starting. 2 pi halves is pi. 3 pi halves, 4 pi halves. This would be 5 pi halves. 6 pi halves would be 3 pi. 7 pi halves. 8 pi halves would be 4 pi. There's 2 cycles. 9 pi halves. 10 pi halves would be 5 pi. 11 pi halves. 12 pi halves would be 6 pi. And then I can go the other direction. Negative pi halves, negative 1 pi halves, negative 2 pi halves is negative pi. This is negative 3 pi halves. And negative 4 pi halves is negative 2 pi. So we just keep counting and simplifying as we go. How many full cycles of cosine do we see there? How many full cycles of cosine do we see? I see at least 3. Do we have more than 3? I see 4, right? Let's go from the left here. From high point to high point, there's the first cycle. And now we get to our main cycle from 0 to 2 pi. There's the high point to high point. There's the second cycle. High point to high point. There's the third cycle. High point to high point. There's the fourth cycle. And it continues on in both directions. And if we needed to renumber the x-axis, we just keep counting by pi halves. All right, let's talk about some of its features. What's the domain of cosine? All real numbers, all real angles again. Yeah. It's the only other one besides sine that has the domain of all real numbers. Every other one of the four has a discontinuity in it, a vertical asymptote. All right, what's the range of cosine? The other way around. -1 to 1. We got to go from low to high. -1 to 1. That's the same. Those two are the same for cosine as it was for sine, right? Sine had the exact same domain. It had the exact same range. That's the same. All right, how about symmetry? Remember, sine was an odd function with origin symmetry. What'd you say, Wyatt? Origin symmetry is rotational symmetry. I don't think this one has rotational symmetry. If you put your finger at the origin and turn it upside down, the local max at 0 becomes the local min. So that's not quite origin symmetric. But what about folding symmetry? Can you fold it on the y-axis and have it line up with itself? Yes, which means it's a what function? It's an even function. Yeah, it has y-axis symmetry. Now here's the consequence of an even function. You're going to love this. Cosine of negative x is equal to cosine of positive x. Remember, for even functions, if you have a negative input, you don't have to bring it out front. You can just what? Forget about it. Remember that? I hope you remember that. Maybe not. Were y'all here for that? That was first semester. If it's an even function and you have a negative, you don't have to bring it out front like you do for an odd function. You could just forget about it. You can just get rid of it. Negative angles and positive angles have the exact same cosine value. That's going to be important when we start sketching. All right, we have a local maximum again, local max and a global max of y equals 1. What else do we need to do? Oh, inflection values. We have inflection values again, right? I'm just going to say inflection values at the axis points. At the axis points. I didn't do my A very well there. Inflection values at the axis points, just like sine. And then what about the end behavior? What would be the limit as x goes to infinity of cosine of x? It's also d and e. In fact, this graph looks almost identical to sine, doesn't it? It looks almost identical to sine. The only difference between this graph and sine is where it starts at 0, right? Cosine starts high and sine starts at an axis. In fact, if I just take this entire graph, if I were to copy it or lift it up with one fell swoop, all I'd have to do to turn this graph into a sine graph is pick it up and move the point where my finger's at here at negative pi halves 0 and move it to the right pi halves, right? Correct? If I pick up this point, this whole graph, and move it right pi halves, I'll have the graph of sine. The phase shift. The sine graph and the cosine graph are exactly the same. They're only out of phase with each other by pi halves. What's pi halves in degrees? 90 degrees. What do we call two angles that only differ by 90 degrees, that add up to 90 degrees? Complementary. Guess what the co and cosine stands for? Complementary. We have sine and its complementary function cosine, which means that those two functions are only off from each other by 90 degrees, or pi halves radians. That's where the co comes from. It doesn't mean reciprocal. Co means complementary. Sine and cosine only differ by 90 degrees, by pi halves radians. Got it? What does co stand for? Cooperation? Complementary. Good. Nice. Nice. Okay, it's written right there, so if you read, you got it. You got it. Okay, so now we have our two new parent functions, Sahala and Chala. Sahala and Chala. We are now ready to sketch simple transformations of Sahala and Chala. Are you ready? I'm ready. You ready? I'm ready. Let's try it. Example 5. Sketch 3 positive cycles of 2 cosine of 3x. Find the new period, and then find and label the new critical values. Okay, so here's Here's the rule for sketching. This is the rule for sketching. You must always show at least one negative critical value. In other words, I always want to see it cross the y-axis in the negative lane. At least one. You can have more than one. If you want to put 2 negative critical values or 3 or a whole cycle, that's up to you. But you always need to show at least one. Now, this also says to show 3 positive cycles. So, in addition to having 3 positive cycles, I need to show at least one negative critical value. It's kind of the rule of thumb. All right. So, let's go through and think about what this graph is going to be doing to the graph of what? What's our parent function? Cosine. So, this is a modified Chala. This is our A value. That's going to be a what? Let's just talk about it in terms of transformation. What does multiplying in front by a 2 do? How do we write it down, though? We don't just say makes it taller. We say vertical stretch by a factor of what? 2. Not only does it make it taller, it makes it twice as tall. The 3, how would we describe it? Horizontal what? Compression. Good. It's inside, so it's the opposite. It's not 3 times wider. It's 3 times narrower. It's horizontal compression by a factor of 3. So that's what we did earlier in the year when we had random functions. We would write that down, okay? But for this problem, they actually mean something different. Let's come over here and collect our information. A, B, C, D, and then P. A, B, C, D. On C and D, I don't put equal signs, I put colons. I'll show you why. What is the amplitude of this function? 2. That's the wave height, which means the graph is going to go 2 units above the sinusoidal axis and 2 units below. All right, what is the number of cycles in 2 pi? 3. I see 3 cycles between 0 and 2 pi. That's just the B value, right? I'm going to ask you that on the test. I'll give you this equation, and it could be a multiple choice question, and the question will say, how many cycles does this graph show between 0 and 2 pi? And all you have to do is say, oh, that's the B value. It's 3. And you answer 3, and you're done with that question. It's the number of cycles between 0 and 2 pi. Now, once you find B, let's jump down to P. P is 2 pi over the absolute value of B. So what's the new period? What's 2 pi over B if B is 3? 2 pi over 3. What's the new period of this graph? Someone can just say it out loud. I'm circling. 2 pi over 3. It's 2 pi thirds. Let's see if that works. From 0 to 2 pi thirds, I see the first cycle. From 2 pi thirds to 4 pi thirds, I see the next cycle. And then from 4 pi thirds to 6 pi thirds, I see the third cycle. What's another name for 6 pi thirds? 2 pi. See that? 0 to 2, 2 to 4, 4 to 6. 6 pi thirds is 2 pi. There you go. So that's the new period. All right, so for C and D, I don't put equals because I want to put descriptions instead. Do we have a C value here? Do we move left and right at all? No, so I'm just going to put none. You can put 0 if you want. What's the D value? Do we move it up and down at all? No, so again, there's no D value, none. So it's 0. Now, if D is 0, you could say the sinusoidal axis is at y equals 0. The sinusoidal, you can call it SA again here. You don't have to say that that's the slant asymptote. You can say that is your sinusoidal axis, is at y equals 0, which is the x-axis, right? Okay, once you have all that information, we're ready to sketch the graph. So here is your y-axis, here's your x-axis. Here's how you want to set up the graph. I always like to do the y-axis first because it's easier, okay? I'm just going to come up here to 2, and the same distance from the x-axis approximately, I'm going to come down there and call that -2. Now, if I don't think it's exactly right, I can kind of modify it a little bit. I'm just going to eyeball yours and make sure that they're roughly the same. Okay, and I'm going to use all the space there. I don't even have to put a mark at 1. I'm just going to put a mark at 2 and -2. Now, here's how you set up the x-axis. This will eventually become the one that gets more complicated when we have phase shifts. But right now, there's no phase shift. So I'm going to come out about right here. If I need to show 3 positive cycles, I'm going to let that be the length of one cycle. So that's going to be what? What am I going to call the length of one cycle here? Not 2 pi, but what? 2 pi thirds. That's one. I'm going to try and fit one cycle between there and 2 pi thirds. Now, I bisect that and I label it. What's half of 2 pi thirds? What's half of 2 pi thirds? 2 pi thirds divided by 2 is just 2 pi 6, which simplifies to 1 pi third, right? How do you take half of a fraction? You either double the denominator like Lawson did, or if the numerator's even, you take half of the numerator. How do you half a fraction? You either double the denominator or half the numerator. I half the numerator here. All right, now we got to do it one more time. Half of that distance, you bisect it, and you label it what? What's half of pi thirds? Pi 6. Guess what the most important number on this graph is? Pi 6. Yeah. If you want to come over here right away when you find the period, you could just find a fourth of the period by dividing by 4 and you get pi 6. That's your quarter cycle counting interval. Every single critical value, axis high, axis low, axis high, is going to be pi 6 away from each other. Now, I'm not done here. Now I can come over here and bisect that, and I can label it, because all I'm doing is counting by pi 6, right? What's that going to be? 1 pi 6, 2 pi 6 is pi thirds. What comes next? 3 pi 6, which simplifies to what? 3 pi 6, which simplifies to what? I'm going to make you do this in your head unless you want to physically write it down on the side. You got to be able to work with fractions, okay? Let's do it again. 1 pi 6, 2 pi 6, simplifies to pi thirds. 3 pi 6, 3 sixths is a half, so that's pi halves. That would be 4 pi 6. Yes, yes? We're just counting by pi 6. Now that I have those marks, I need to add more. Now, on a test or a quiz, you're not going to be able to just copy and paste those marks successfully. So we need to be able to create new marks by what I call the eyeball method. This distance right here between 0 and pi 6, because 0 is a critical value, you need to preserve that the best you can. So let's just go ahead and add a few more marks. So I'm just going to add marks roughly the same distance away. And again, I'm just eyeballing it. How many more do I need? 1, 2, 3, 4, 5, 6, 7. I think I need one more. There we go. Now, I'm going to make you label those. Every critical value has to be labeled, every single one of them. So what am I going to do? I'm just going to keep counting by pi 6, and I keep simplifying. So 1, 2, 3, I'm at 4 pi 6. What comes next? 5 pi 6. 6 pi 6. What's that? 6 pi 6 is what? Pi. We'll stop at pi. That's a good place to stop, at pi. Actually, I like to start at pi. Pi. Okay, thank you, Jasmine. We just ran out of time on example 5. We'll finish this tomorrow after our next quiz.